In this video we are going to discuss survival analysis, and the first part is focusing on calculating the Kaplan Meier estimate. But before we do that, let us take a small recap and go back to longitudinal studies. As you might remember, longitudinal studies are studies where participants are followed up over time, and these participants contribute multiple measurements over time. In this type of studies we are often interested in incidence, which means that the individuals also need to be event-free at the start of the study. And when analyzing these studies, we assume that the outcome is related to the exposures during the follow-up. This is in stark contrast to cross-sectional studies where exposure and outcomes are actually measured at the same time. So this is an example of a longitudinal study. It's a study conducted with 757 gay men who are followed up over a period of 5 years, and the outcome was the incidence of HIV infection. After 5 years, there were 97 infections recorded in this cohort. So what is the risk of HIV infection in this cohort? The cumulative incidence, the risk, can be seen as the number of events divided by the total population of the cohort, which would make 12.8%. But by doing so, we are assuming that each of the participants is followed up for the full duration of the follow-up. In this schematic representation, we have 10 participants followed up over 24 years, and only at the end, at month 24, the outcome is assessed as being either present with an X or not present, denoted by a 0. So the epidemiological fraction at the end of follow-up is the number of new events divided by those at risk without When we talk about risk, we actually assume that all the participants have been followed up for the full duration of the follow-up period. In this schematic representation, for example, we have 10 participants, denoted by the blue bars, who are followed up 24 months, denoted by each of the columns. And the outcome is assessed for each person at the end of the full 24 months of follow-up. They either have the outcome, denoted by an X, or they do not have the outcome, denoted by a 0. We can then calculate the epidemiological fraction at the end of follow-up, which is the number of new events divided by those at risk, those without an event at the start of the observation period. And that gives us the incidence risk, or the cumulative incidence. But as said, the cumulative incidence, or the risk, has some assumptions. The main one is that the follow-up is complete for all participants. If there is attrition, so people who are leaving the study, this is completely ignored. Everybody is event-free at the start of the exposure, because that's part of the definition of the incidence. And the risk starts only accumulating after the start of exposure. But we have seen that it's often not the case. We are more likely to deal with a dynamic population. That's a population where people leave the study during the follow-up period. So not everybody is being followed up until the end of the follow-up period, like denoted on the left. In addition, it can also be that people enter the study late, not all at the same period in time, but actually during the follow-up period, which is denoted on the right. The first situation we call attrition, loss to follow-up, and in the second situation we have both attrition and a staggered entry in our study. For dynamic populations, we formulated our epidemiological fraction slightly different. We still look at the new events occurring during the follow-up, and we still look at the people who start the follow-up without an event. But the denominator changes. Instead of the total population, we will take the total observation time, which gives us an incidence rate or incidence density, the number of new events during follow-up divided by the total follow-up time in the population at risk for the event. So actually we add each of the blue squares to come up with the total follow-up time in our cohort. This is already better, but assumptions are also there. It assumes that the underlying risk of the event is actually constant during the entire follow-up, which means that my risk of the event is the same if I being followed up in the first 6 months compared to being followed up in the last 3 months. And we know that also that is often not true. For many occurrences, there's an increasing risk with age. And that is especially important when we are dealing with very long follow-up, those so-called birth cohorts, where they follow up everybody born in a certain year or a group of years. An example of that is a long-running Millennium Cohort study. We also know that the risk can change suddenly due to comorbidity. For example, the risk of tuberculosis for somebody increases massively when that person becomes HIV infected. But the risk can also decrease over time because a person starts therapy. For example, let us look at this cohort where every gray bar denotes a single person. An X is the occurrence of an event and a 0 is the occurrence of a loss to follow-up, of attrition. And each gray block stands for 1 month of follow-up. So if I oversee the full length of follow-up, we can calculate that there are 6 events in 126 months of follow-up. If we sum all the gray blocks, we come to 126. And just mathematically, that translates into 0.047 events per person month, or 0.56 events per person year, or 56 events per 100 person years. So the rate or incidence density can be expressed in any form of the time, whether that is a person month or a person year or 100 person years, or any other form that you might like. But what would have happened if I looked at the rate if I only looked at the first 12 months? Here I have only 2 events in 73 months of follow-up, which translate in the end to 32 events per 100 person years. So quite different than when I looked at the full 24 months of follow-up. And the same holds true when I look at only the first 6 months, because there my rate is actually 0. There are no events. If I look at 1 month of follow-up, it is still 0 because there are no events. So from here it follows that 1, the risk can only be interpreted if you know the time frame, but also that the length of follow-up period becomes irrelevant as long as there is no occurrence. It didn't matter when I followed up 1 month or 6 months, the rate remained 0. And here we start defining the concept of failure. So I have been talking about an event which is actually the outcome of interest, and in survival analysis we call that a failure. And dropouts, like somebody being lost to follow-up, is called censoring. So the terms failure and censoring are central when we talk about survival analysis. So after this short repeat of the concept of incidence density or the rate, we turn to survival analysis ourselves. So survival analysis actually cuts up the follow-up period in small pieces that end when an occurrence happens. As long as there's no occurrence, the observation period continues. And when there's an occurrence, for that observation period, I calculate the risk in each of these time periods. So the number of events divided by the number of persons at risk in that event. And the survival analysis then combines all these incidence risks from all time points and put them together in an overall survival, which is the proportion of the population without the outcome. And by doing this, survival analysis combines risk and rates in a survival estimate that takes care of the fact that not every person is being followed up for the full period of time, and that the risk within certain periods can actually change. And that is the main advantage of survival analysis. It deals with the two major assumptions that are there with the incidence risk and the incidence rate. So then let us look at a numerical example. We have a very small cohort that is followed up over 8 time periods, and we have 1, 2, 3, 4, 5, 6 participants followed up in these 8 periods. And they either have an event with an X or they do not have the event with a 0 but are lost to follow-up. And for each of the period we're going to calculate the risk of occurrence in that period. So our first period is the baseline at time point 0. Then how many people are there at risk? That's actually the start of my cohort, so all 6 people are at risk. And of course all those people are event-free, so they survive for 100%. And survive means not having the event. So when is the next event happening? The next event happens at period 2. And how many people are then at risk at period 2? Well, that are the same 6 people, because everybody was event-free until the end of period 0. And what happened at point 2? That's actually a failure. One person failed and nobody was censored. Nobody was leaving the study. So that means that by the end of the period 2 or at period 2, the probability of survival, the probability of not having the event, becomes 6 minus 1 divided by 6. Because one person failed, so 6 minus 1 survived. And my at risk was 6, so the probability of survival at time point 2 was 5 divided by 6. From then we go to the next event. When does that occur? It actually occurs here at period 4. How many people were then at risk of period 4? Well, that will be 5. Because I have only 5 persons left in my study that do not have the event. This person that failed in the previous episode is now not at risk anymore for the event, because that person already had the event. And what was the time of the event? There was actually failures. 2 people developed the outcome. 0 people left the study. So then what would be the probability of survival? That is 5 minus 2. 5 were at risk, 2 failed, therefore 3 survived, and survived is not having the outcome, and the period started with 5 persons. So the probability of survival at period 4 was 3 divided by 5. The next time an event happens is at period 5, here. How many people were at risk? Well, that were actually those 3 people that were survived until the previous period. They started a new risk period. And what happened at that failure, at that period, period 5? Well, somebody left the study. Nobody developed the outcome, but somebody left the study. So then what is the probability of survival at period 5? Well, I started with 3. Nobody developed the event, so all of these 3 survived. Survived meaning not having the outcome. Divided by 3 is 1. So everybody survived that period without an event. The next time an event happens is at time point 7. How many people were now at risk? Well, that's actually 2, because this person left the study, is no longer there. So I only have 2 people who were at risk at period 7. What happened? There was a failure, therefore the probability of survival equals 2, the ones who started, minus the 1 failure, divided by those who started, is 1 divided by 2. And the last period is period 8. How many were at risk? That were actually 1, because this person is now no longer at risk. What happened there? There was a censoring, because it was the end of the study. How much was the survival? That is those who started minus the failure divided by those who started is 100%. And by looking at each and every period separately, assessing how many people are at risk at the start of the period, assessing what happened in that period, is there an outcome called a failure, or is somebody leaving the study, we can calculate for each period the probability of survival. So with a table like this, we can actually calculate the probability of surviving, for example, until the end of period 4. To get there, you first need to survive period 2. And then you need to survive period 4. So these probabilities depend on each other. They are conditional, and therefore standard mathematics stipulate that we have to multiply these probabilities. So the overall survival until the end of period 4 will be 5/6 times 3/5 equals 50%. Similarly, the probability of survival until the end of my study, the end of period 8, is multiplying all these probabilities for each time period. So 5/6, 3/5, the period that everybody survived, and in the end we come to 0.25. 25% of the cohort survived, had no outcome. by the end of the study. So, and this multiplication we call the Kaplan Meier estimate. So it is the probability of survival, and that probability, as you could have seen, is only affected by failure, by outcome. When the event was censoring, a 0, a loss to follow-up, it only resets the number at risk for the next period. We saw those 2 periods where the survival was 100%. Why? Because that period was defined by the occurrence of loss to follow-up, censoring. Yeah? So the Kaplan Meier estimate combines all probabilities of survival from infinite small time bands, time periods. And it assumes no underlying distribution of failure time. So in that sense, it is a non-parametric approach. The table that we have just constructed with all the different probabilities of survival in the time periods, from that we can also make a graph. And then we get this typical Kaplan Meier curve, which is a stepwise curve downwards that plots the probability of survival on the y-axis with time on the x-axis. And sometimes people plot the number of people censored also on the graph, like done here with 1. One person was censored at period 8 and one person was censored at period 5. And that shows clearly that censoring or loss to follow-up does not change the probability of survival. Censoring only resets the number at risk for the next period. The Kaplan Meier curve is sometimes also displayed as a cumulative incidence curve, where it is turned around and mirrored, which then shows the analysis time and the proportion of persons having the outcome. It depends a little bit on your research question which curve is more useful. But they display actually exactly the same information. This type of curve you will see in the scientific literature very, very often. And one of the most important of these Kaplan Meier curves from the last 2 years is actually this one. This is showing the result of the first vaccine trial of the COVID vaccine. The authors has chosen to use the form of the cumulative incidence. So it plots the proportion of people in the vaccine group compared to the control group who got a proven COVID infection after the start of the trial. And you clearly see that those who are not vaccinated have a much higher incidence over time for COVID infection, a proven COVID infection, compared to those who did got the by then still experimental vaccine. This brings us to the end of part 1. In part 2 we will talk about how we can compare the survival probabilities of different groups.